Hello everyone, I'm Bianca Marchionna, a PhD student from the University of Milano-Bicocca. First of all, I want to thank all the organizers for this opportunity. And in this video, I will talk about some double-coset zeta functions for groups acting on trees. It is a part of my future PhD thesis. So first of all, what are double-coset zeta functions? They are series depending on a complex variable uh, recently introduced by Castellano, Gianmarco Chinello, and Thomas Weigel. In detail, we fix a totally disconnected and locally compact group, G, in short a TDLC group, and also a compact open subgroup O of G. For instance, G might be SL2QP and O SL2ZP. And then the associated double-coset zeta function depends on the complex variable S, and fixed S is the sum over all O double cosets OGO of the cardinality of OGO over O at the power of minus S. This is regarded as a quotient space. In particular, we'll be interested in the case when G acts on a tree. But before going on, let me fix some notations. When I say a tree, I mean a connected and acyclic undirected graph, T. And Vt and Et will be the set of vertices and edges of T. I will also assume that T is always locally finite, that is, every vertex has only finitely many neighbors. And as already anticipated, we will be interested in TDLC groups acting by tree automorphisms on a locally finite tree with compact open vertex stabilizers. This last assumption is motivated by the fact that in a zeta function we want to choose O as a vertex stabilizer. Before going on, another technical assumption. I will always assume that the edge pointwise stabilizers are both contained in the stabilizers of the endpoints of the edge. So some examples. The most natural one is the whole group of three automorphisms of a locally finite tree T, that is the set of all self-bijections on Vt, preserving the adjacency relations on the tree, and it is a natural TLC group with the permutation topology. It is the group topology generated by the subbased 1 given by vertex stabilizers. These vertex stabilizers are clearly open, but they are also compact because our tree is locally finite. More generally, we can consider subgroups, closed subgroups of OT as possible examples. Another famous example is SL2QP acting on its vertex building, that is a P+1 regular tree, and vertex stabilizers are up to conjugation and up to isomorphism SL2ZP, so compact and open. Returning to the double-coset zeta functions, we fix the environment we will work from now on. So G will be a TDLC group acting on locally finite tree T with compact open vertex stabilizers, and we will fix O as an arbitrary vertex stabilizer. Under these assumptions, we have a one-to-one correspondence between the double cosets OGO and the O orbits of geodesics from V to GV. I remind that given two vertices, there exists a unique geodesic in our tree connecting them. In particular, our target cardinality will be exactly the cardinality of this O orbit. So computing double-coset zeta functions in this case becomes a more combinatorial problem. However, in general, it seems to be hard to find a unified approach for computing these quantities. Assuming some transitivity properties on the action, we will see that we will be able to express a formula of these quantities in terms of local data of the action. In detail, we can observe in this general setting that every geodesic from V to GV, where G is arbitrary in G, induces a loop in the quotient graph based at pi V, that is the image of V on the quotient graph. And more precisely, we have a surjective map from the set of all geodesics from V to another vertex in the same G-orbit onto the set of all loops at pi V in the quotient graph. if these maps are all bijective for every V, then we say that the group G acts weakly locally infinite transitively on T. Why this name? It is inspired by another well-known property, these locally infinite transitive group actions on trees, and indeed one can prove that if the group action is edge transitive, then this concept is exactly this one, locally infinite transitive actions. And so we have an important subclass satisfying this property. There are also some groups that lie in this class but not in this one. For instance, color-preserving automorphisms of locally finite trees. Groups of color-preserving automorphisms of locally finite trees. Returning to the zeta function, if we assume furthermore this transitivity property, we can refine our one-to-one correspondence discussed above as follows. So every double-coset OGO is in one-to-one correspondence with a certain loop in the quotient graph, and our target quantity is exactly the number of geodesics in T from V lifting that loop. And so this quantity can be computed only by knowing the quotient graph and how many lifting any edge of the quotient graph admits, which are local pieces of information that are potentially easier to cope with. So with this, and assuming that the quotient graph is finite, we can find an exact computation of our zeta function all semi-homomorphic continuation. In particular, we can evaluate this zeta function in potentially every point of the complex plane. The value -1 seems to be particularly interesting, and the motivation is the following result of Castellano, Chinello, Weigel. So let G be a simply connected Chevrolet group scheme evaluated in a non-Archimedean local field, and O be any parabolic subgroup of G. Then the value of the zeta function -1 is related to the Euler characteristic of the group with respect to a fixed arbitrary Haar measure mu. And the exact relation is expressed in this following equation. Inspired by this, we are then able to characterize when this equation is satisfied in our setting. More precisely, it is satisfied if and only if the quotient graph of the action is a tree. This geometric characterization can be furthermore refined if G has the Tits property P and it is non-compact, because it is satisfied if and only if the group is simple. The abstract simplicity arises also in the study of other analytic tools of the zeta function, for instance, the approaches of convergence. And more generally, all the machinery introduced for computing these double-coset zeta functions can be used for studying other invariants of the group, for instance, the Willis scale function. And with this, I've finished, and thank you for the attention.